Good morning. Today we're going to discuss about the forward and inverse kinematics using the Denavit-Hartenberg Convention. So this is the in connection, or this is the extension of the discussion that we had before for MCTE 521 robot motion planning class. So today we're going to do some exercises. So in the board, I'm showing one of the robot examples in the book of, in the robotics book of Siciliano et al. And we're going to derive for this 3 degrees of freedom robot. This is considered to be an anthropomorphic arm. That means it's similar, its physical characteristic is similar to that of the human. I think, if I'm not mistaken, this is the shoulder part. And we are going to derive the DH convention for this. And we're going to compute the inverse kinematics. I mean, the forward kinematics for the first part of the lecture. And then for the second part, we're going to solve for the inverse kinematics. So let's start by solving. And this is the DH parameter convention. And I have modified the arrangement of the description of DH parameters for easy understanding. And I have here with me also an octave, or just similar to MATLAB, that we can compute. I will make use of it as a calculator. And here underneath is the solution. So we'll check later whether we're going to get exactly the same answer. So let's start. Let me do the annotation. Where's annotation? Okay. So let's start by assigning, let me draw the z-axis. Oh, so it's here already. So let's just trace one more time and see if we can understand it correctly. So we see here in the convention that we have, oh, I cannot click. Okay, let me click there, then annotate again. Come on, annotation. Okay, let me just draw. I think drawing will be much better. So we have joint I rotates about zi minus 1. So where is joint 1? So this is joint 1. So we say that this is theta 1. Okay, rotating about that axis. And so that means that z0 should be along this axis. So we can say z0 will be along this axis. Okay, and there, in fact, this is z0. Okay, so that's the axis z0. And we say that now we're just going through all of those z-axis or z-axis if you are British. And so this is theta 2. Theta 2. Okay, it rotates about this axis. So positive direction will be, let me just show my face here, so that positive direction will be in this case. So now positive direction is in this case. So this is Z1, okay, where joint 2 is rotating, okay, and then this is that is joint 2, and where is joint 3? Joint 3 is again rotating about Z2 axis, so this is joint 3. So positive direction will be in that direction. That is your Z3. I know, Z2, and this is your theta 3. Okay, and then again, this just label it to confirm that you have identified it. Okay, so we have identified the directions of all the z-axis. So now we want to know where is the x-axis. This is the first step that you need to identify. Then where is the x-axis corresponding to all of those z-axis that we identified? So now we identify, oh sorry, this is z0. Okay, So we identify Z0 already. We want to know where is the X0. Okay. For the start, for the base of the robot, we can choose arbitrarily where is the X and the Y, where is the X axis. And so the Y-axis completes the right-hand rule. And so we say, for example, we want to have the, we can choose to have the X-axis here. Okay, if that is our X0 axis. So that means if we choose our X0 axis to be there, we are saying that the origin of the zeroth frame is here. Okay, the origin, and then completing the right-hand rule. That means your Y will be here. Okay, that's Y0. Okay, and the origin is here for frame 0. Okay, so now we're not violating anything because the base frame, X and Y, are just arbitrary. Okay, now let's go to the X1 axis. Where is X1 axis? It says X1 axis is common normal, okay, over here, common normal and intersecting to both Z1 and Z0, or Z1 and Z0, okay? So where is Z1? Well, Z1 is here, okay, and Z0 is here. So common normal. So common normal meaning right-hand angle to both axes. So there's no other common normal except for in the direction where you cross them, okay? So if you cross Z0 and Z1, of course, the common normal is along this direction. So this is already, that's X1, okay? Where this is common, normal, and intersecting. So in this case here, this is normal to Z0, okay? We can be somewhere here, okay? Normal to X1 has to be normal to Z0, yeah, that's normal to Z0. And also, is that normal? X1 can be here, okay? Because that is normal to Z0. And is this also normal to X? Is X1 also normal to Z1? Okay. Yes, it is also normal because we can have this is parallel, and so this is normal. Okay, X1 is normal to, in this case here, this is Z1. Okay, parallel to Z1. But in this case, are they intersecting? It's not intersecting, and so we cannot use that. So we have to erase it because this is not intersecting. Okay, so we have to intersect, and so here we have to move it downward here so that it will intersect. X1 will intersect with Z1. Okay, so really our X1 should be here because here X1 intersects with Z1. It's normal to Z1 and intersecting. Is it normal to Z0? It's normal to Z0. Does it intersect? Yes, it intersects. So for in this case, X1 can be anywhere. Let me just do this. In this case, X1 can be here, can be here, can be here, and all of them are intersecting and perpendicular to or normal to Z0. But is it normal to Z1? Yes, these axes, all these lines are normal to Z1, but are they intersecting to Z1? But no, they don't intersect Z1, so that's why you have to move this axis to here in order to identify this point as the point where of origin of frame 1 that locks the origin of frame 1 into this point. Okay, so now we have identified the origin of frame 1, and we have identified in that sense we also identified the direction of X1, and so now we are complete with the frame 1 axis, and so Y1 will be just the right-hand rule. By the right-hand rule, X1 is there and Z1 is in that direction, and so Y1 will be up here. Okay, y1 will be in this direction. Okay, so the origin of frame 1 will be there. Okay. Okay, now let's encircle those origins so that we can see them. So this is we cannot see it. Okay, anyway, let's just maybe this one pink is very clear. Okay, or we don't do this one so that it's clear. Okay, that's the origin of frame 0, origin of frame 1. Okay, now where's the origin of frame 2? Origin of frame 2 is, again, we identified already where is your Z2 is here. And so where is our X2? X2 is again normal to both Z1 and Z2, okay? And later we have to satisfy the intersecting requirement. So X2, so if this is Z2, X2 can be here, that's fine, that's normal. Okay, and X2 can also be here. Okay. X2 can also be here. That is also normal. Okay, but where is it? It has to be normal to, this is X2, yeah? So it has to be normal to Z1 as well. Where is Z1? Z1 is this, okay. Is this normal to Z1? Is this normal to Z1? Yes, this is normal to Z1, okay. Is this axis normal to Z1? Yes, it is normal to Z1, yeah? So now the question is, are they, in this case, these two axes are intersecting, okay? These two axes are normal and intersecting to Z2, but are they normal and intersecting to Z1? No, okay. So which one can be normal and intersecting to Z1? So if we transfer this axis, we transfer it over here. Yes, it is normal and intersecting to Z1, but is it normal and intersecting to Z2? It is normal to Z2, but it is not anymore intersecting to Z2. Okay, so that means that this one does not satisfy both requirement of normal and intersecting to Z1 and Z2. What about this one? It's normal and intersecting to Z2, yes, but then is it normal and intersecting to Z1? Because we can extend it. This is an axis, we can extend it to here. So is it normal? Yes, it's normal. Does it intersect to Z1? Yes. So that means that this axis satisfies both the condition of normality and the intersecting requirement. So that means that this is our X2. Okay, so let's erase the other ones. Let's erase this. We don't need this. Okay, so now where is your Y2? Y2, okay, let's remove that. So Y2 completes the right-hand rule, and so that's X1 and X2, and so this is the correct. Y2 will be up here. Okay, so now where is the end effector? So where the end effector will be somewhere, because this is the joint, so there will be some extension, okay, from the joint, and the link length of, normally there's a link that is associated to that joint, and so if we say that this is the link, then we put the end effector here, and normally the convention is that you extend you assign, or you extend the joint n-1 reference frame into the nth frame, okay, without any rotation, but just translate along the end effector. So now if we translate it along the end effector, so this is Z3, and so and this is Z2. So we transform this up to the n effector. In this case, this is, we identified for the n effector, it's normally, it doesn't hurt. Again, it can be arbitrary. We identified already the frame to origin to be there. Okay. And frame 3 origin, we can arbitrarily, because n effector and the base frames can be arbitrarily selected. I mean, their n effector points can be arbitrarily selected. So we select that. That is our frame 3 point. Origin of frame 3. Okay. So now we say that we just copy or translate the n-1 reference frame, and so without any more thinking a lot, so that's xz3, and this is x3, the same as x2 direction, and this is y3. Okay, so we have confirmed those directions from the drawing of the book from Siciliano. Okay, now we have identified how we attach the frames. So we are ready now to derive the Dh parameters. So let's check what are the Dh parameters. Okay, so theta 1, okay, let's have some convention here. We can have a table. Okay, let's have a good text so we can. Okay, theta, or maybe Q, Qi. Okay, and then you have alpha. How to say alpha? Q. I don't want to use A because alpha. Okay, alpha I, and then you have AI, DI, and AI. Okay, and here we are going to put I. Okay, so that's our the things that we need to identify. Okay, now, so we'll have for joint I, joint 1. So for joint 1, we have theta 1. Of course, these are all the variables because the joints are revolute, so we can have theta 1, theta 2, and theta 3 there. Okay? No need to think. That's what it is. Okay? These are the variables. So now let's do alpha. Alpha I is, so theta I, yeah, let's just go through the convention, just one. From about Z0, so about Z0, where is it 0? That's Z0. And theta 1 goes around that direction. So this is theta 1 goes about direction from xi minus 1 to x. Where is xi minus 1? This one is xi minus 1 to x0 to x1. So from x0 to x1 in that direction, that's positive. Okay, theta 1 is positive. We know that because we already identified the direction of z to be in the positive direction of your theta. So that's fine. So now all of them are positive. So in this case here, this is z1, and so theta 2 is in that direction, positive. Okay, is this from, where is your x? Okay, theta 2 is from theta 2 is from about Z1 is about Z2 from, about Z1 from X1 to X2. So where is theta 2? About Z1, that is Z1, okay? From X1, Yes, from x1 to x2. Where is x1? That's x1. And where is x2? X2 is in that direction. So here, because this is not, there's an angle here. This is not 0. And so in this case, theta 2 is equal to 0. I mean, theta 2 is equal to this displacement there. If it was 0, then this whole axis will be parallel, will be coincident with this axis. So now that's fine. And then theta 3 is about Z2. Where is theta 3? This is theta 3, and that is Z2, and that's positive, correct? It's positive in the Z2 direction. And so from X2 to X3. So where is X2? This is X2 to X3. Again, X3, there's some angle from here to there, from here to there. Okay, which is the angle of your theta 3. Okay, if this one is down here, they're coincident, then theta 3 is equal to 0. That's fine. Okay, so now let's go alpha I. So alpha 1. So alpha 1 is about x1 from z0 to z1. Okay, where is x1? Okay, let's go first about x1. Where is x1? There's x1. Okay, so x1, about x1 from z0. Where is z0? So that is your x1, and from, in this case here, from z0 to z1. Okay, from z0 to this one, that means from there move to here. Okay, about x direction, about the direction of this x. So that means it's a positive direction. It's positive, and it is what? 90 degrees. Okay, so alpha here is 90 degrees. Or we can say pi so that it's easy. Okay, undo. Okay, there. Pi, positive. Next, we have join 2. Okay, alpha 2, about x2. So where is x2? This is x2. Okay, from z1 to z2. Where is z1? Z1 is here. Okay, z1 is here, about here, z1 to z2. Where is z2? Z2 is here. So about, is there any rotation of x2 when you go to from z1 to z2? No, this is 0. So if this is just a little bit confusing because there is this angle movement, but if you make this axis coincident to there, because join 2 moves in this case, if this axis coincident to here, so we can clearly see that x2 and z2 and z1 are not moving with respect to each other. There's no offset, angle offset with respect to each other in terms of the rotation about x2. So this is 0. Okay. Next, alpha 3. So it is about x3. So where is x3? This is x3 from z2 to z3. So where is z2? Z2 is this one. And where is z3? Z3 is this one. Again, these axes are parallel and there's no rotation about x3. And so that is 0. Okay. So next, we go, that's theta and alpha are finished. So D1. D1 is along Z0. Where is Z0? This is the one. From origin of the zeroth frame, origin of the zeroth frame is this one. Okay. Origin of the zeroth frame to the intersection of Z0 and X1. So that is Z0 and X1 is this one. So that is the intersection from here to there. So along the Z0 axis, Z0 is in that direction from here to there. So that's a positive direction. And so we can assign this to be A1. Okay, it's not assigned. A1. Okay. So here, do they say, okay, D1. Let's just say D1 because that's a D direction. Okay. We can have, so that it's not confusing, just say A1. Uh-huh. Hmm? Okay, say A1. So all the distances, we assign it to be A. But luckily, there's no D. Cool. Is it better? Okay, let's just say A1, yeah? And then, so along, okay, what about D2? D2 is along Z1. Where is Z1? Z1 is here along Z1 from origin of frame 1. So this is origin of frame 1 to intersection of Z0 and X1. So Z0 and X1 is this one. So again, along Z0, sorry, you are looking at D2, yeah? So D2 along Z1, this is Z1, origin of the ith frame, okay, origin of the first frame. So this is origin of the first frame to the intersection of Z1 and X2. So Z1 and X2 in this case, because you are looking at D2. So Z1 and X2, that is the intersection, and it's coincident with the origin of the frame 1, and so that is 0. Okay, next. D3. So D3 is along Z2. Okay, where is Z2? In this case, here is Z2. So from origin of the 2 frame, okay. So origin, this is the origin, to the intersection of Z2 and X3. So that is X3, and its intersection coincide with the origin of frame 2. And again, this is 0. Okay, maybe to make it sure. 0, we'll put 0. Okay, we're done with this one. And then alpha 1. So for alpha 1, I mean A1, along X1. So where is X1? This is X1. Along X1, from origin of frame 0, okay, origin of frame 0, origin of frame 0 to intersection of, no, sorry. Okay, this is A, yeah? So we're looking at A along X1, this is X1, from intersection of Z0 and X1. So intersection of Z0 and X1 is this one, okay, to the origin of frame 1. That intersection is also the origin, and so that is 0. Okay, A2, along X2. Where is X2? That is X2. Okay, if this one is didn't move, then X2 and X1 are coincident. So along X2, from intersection of Z2, Z1 and X2. So Z1 and X2. So this is X2, and where is Z1? That one. This is Z1. This is Z1, and that is X2, and this is the intersection. Okay, intersection of Z1 and X2 to origin of frame 2. So from here to origin of frame 2 is here. Okay, from here to here along X2, and this is X2, and so that is the positive direction, and so it is A2. Okay, let's delete something. Let's delete. Okay, and make. Okay, so now the last one, A3. A3 is along X3. So where is X3? X3 is there. X3 from intersection of Z2 and X3. So where is Z2? This is Z2, and intersection of X3 is this one. Okay, that's the intersection with X3 and origin of frame 3. So origin of frame 3 is this one. So along X3 from here to there, from this intersection to the origin of that frame. So that is A3. Okay, we're done. So we're done with the Dh convention. DH assigning the DH convention for the attaching the frames. And then now we look at the DH parameters, and let's see if we have done correctly. Okay, so link 1, A1, okay, this is A. So the A's are 0, A2, A3, that's correct. And then the D's, A1, 0, 0, theirs is 0. You know the reason why? The reason why is because, again, we say that the base frame can be arbitrary. Okay, the base frame can, in their case, the base frame is assigned to here. This is the origin of the base frame, and so they don't have any offset here, A1. Okay, because for us, we put our base frame to be here, and so we have an offset of A1. So that's fine, but the rest of them are 0, 0. That's okay. What about alpha? So alpha is pi over, yeah. It's pi, 90 is pi over 2. Yeah, it was 90 before, and I changed it to pi, my mistake. So we have to put pi over 2. Sorry, pi over 2. Okay, so pi over 2 and 0, 0, that's fine now. And then the rest of them are all the variables, theta 1, theta 2, and theta 3. It's okay. So now we have successfully derived the DH parameters. So now, for example, we are given that we are going to use MATLAB now. Okay, so we know that the DH. Now let's go here. Okay, so we have to make a rotation. Okay, I should come out with okay, so rotation Rx. Let's just say Rx. So rotation of Rx is what? Cosine. I have to put theta. Is equal to, for example, 10 degrees, okay, times pi divided by 180 to make it into radians, and then Rx, rotation about x, is equal to 1 cosine of theta, okay. Is x theta? No. What is the normal convention? We will say, I know x, z is about theta, and alpha, and what about x? Phi. Okay. X is alpha, and then beta is, what do they have? I want to follow the convention for, we have it in the previous slide. Let's see. I want to use the same convention in the angle. Lecture slides, position, and okay. So they're using X. Okay. I want to use the same convention as they have. So they're using X alpha, and then Y is phi, and Z is theta. Okay, so we'll use that. So here, so for X is alpha. Okay, I'll use here alpha. Alpha, okay. And, sorry. So this is 0 because this is rotation about X, that's 0 and 0, okay. And then the other, what about also that's 0, and then cosine alpha, that's the middle term, okay, and then minus sine of alpha, okay. Here I should make it alpha, okay, and then the last row will be what is that? 0 again, and then sine of alpha. alpha, and then cosine of alpha. Okay, so let's check. Eh? How come I cannot enter? This one. There. So that's correct. Around x, that's all 0. And then this is cosine minus sine, and then sine and cosine. Okay, that's x. And then now let's rotate about y will be phi. Okay. So if we rotate about phi, and then we'll just put arbitrary numbers there so that we can compute later. We can use it function. We can use this function to compute later. Okay, let me extend it a little bit. And then you have, because you are rotating about y, so here, okay, that's negative, and then this one is 0. Okay, no, 0 here because it's about y, and this is positive. And then the second row will be negative sine. No, it's not alpha, but this is phi. That's phi, and this is phi. And now this is phi. And now this is phi. No, about y, so that's 1, and this is phi. Okay, and then the second row, and the third row is sine. Okay, sine of phi. Okay, 0 and cosine of phi. Correct? Yeah. Okay. The diagonal terms are cosine. The off-diagonal terms are sine, and then minus sine for the second row, and positive. I think that's correct. How come there are two signs? No. Wait. That is 0 because y. This is rotation about y. Okay. So y will be 0, 1, 0. And up there cosine 0. And okay. Now here, down here is minus sine. And then 0 cosine. Yeah, correct. So that's negative. Okay. The same as the sine convention. I mean, the cosine rotation about x is negative and positive. Here will be this is negative and this is positive, and the cosine is here. Okay, that's why. Okay, now let's solve theta. This is rotation about y. Okay. Okay, so the other one is rotation about x. Rotation about x. Okay, just to correct it. And so now we have rotation theta about y. So rotation theta about this is about z, rotation theta, and then now cosine, and this is sine, and that's 0. Okay, and here will be minus sine and cosine and 0 and 0, 0, 1. Okay. Yeah, that is z. So now, okay, so that's your rotation on z-axis. So now we need to know using this convention of Dh convention. I need to have the okay. So yeah, I want to follow. Okay, I made the rotation matrices, and then I need to do that to compute for the transformation matrix. And so if we need to compute, okay, we have transformation, transformation x by, okay, by x by phi, okay, is equal to, okay, because we are, okay, no, we want to follow, I want to follow this convention here. So transformation, I just want to follow this one so that we can, so transformation of x by alpha, okay, where is x by alpha there? So x, Rx, Rx, and this is 0, okay. No, we need to have, let me check with this one, 0, 0, 0, okay. And then at the bottom, you have 0, 0, 0, and 1. Okay, let's check. Yeah. So your Rx need to be computed. I think I need to create functions here so that I can easily compute the, yeah, by the way I'm doing it is a lot of work. So let me stop now, and then I will try to make functions so that we can easily see. Because right, I wanted to do the manual computation so that you can see exactly the struggle of instead of showing you the pre-computed code. So I will make a code later. I will stop now, and then I will make a code later so that you can easily follow. Okay, let me stop. Let's continue. So we are now, as I promised, we are going to make a forward and inverse kinematics using functions so that we can easily see what's the type of computation that you will need in your exercises. This again, this is for MCTE 512 robot motion planning. So in the previous session, we already derived the Dh parameters by assigning the frames for each joint for this anthropomorphic arm, and which only considers the shoulders. And this is the bigger picture. So we derived Dh convention and the Dh parameters, and so we can say that in the table we have already confirmed our solution to be correct. And I think the only difference that we had was in this case here, the D1, you have, maybe in this case, we'll just put D1 so that it will be according to the convention. So you have D1, well, the rest will be the same. So we assign our X, your Z0 to be there, and your X0 to be here, and your Y0 will be here according to the right-hand rule. Okay, so now we are going to compute the end effector of the robot for any arbitrary joint values. So I have created here, this one. I have created here a file that computes robot kinematics. So in this case, it will accept theta, alpha, D, and A, which are the Dh parameters. And we are going to compute the end effector position and orientation for any arbitrary joints, and also for any Dh convention, for any robot with a given Dh parameters. So that means that the size of the robot in this case can be changing. So let's first see M and N, the size of the robot that we give, and so we just say theta. Okay, we'll just accept 1, and then we get n to be, okay, maybe mi and ni and ni. So number of joins will be n, and links, or maybe just n so that we can easily, and then it will be the maximum of mi and ni. We need this just in case the person entering is has the vector transposed, or a column or a row vector. So we'll see, and so we know that this it inputs a vector. So maybe we see here inputs accepts vectors of dh parameters. Okay, so all of them are vectors, and then we determine the number of joins of the vector by the size of the vector. Now, number of joins of the robot by the size of the vector. So now let's we already have the Dh convention here, and so we're going to compute the forward kinematics. This is the transformation matrix. So for any given transformation matrix, we'll create a transformation matrix A. Okay, so function transform, or maybe A, and then again, and then you input the same input, theta and alpha. And then if you're given like that, we will be able to compute for the okay, let's compute. So we will base our transformation here, transformation matrix. And so let's just compute the rotation of Rx, basic rotation function. Let's compute the basic rotation just like what we did. And Rx, rotation about X, Rx, what is this? Rx alpha. Should we say alpha? Rx alpha. Okay, that's fine. And so this is function Rx alpha, and so it accepts alpha. Alpha, okay, and then end function. Okay, and so we say that we return Rx alpha, okay, this is basic rotation X around alpha. Okay, so now Rx alpha, Rx, or maybe just say rotation about X, that's fine. Okay, is equal to 1, 0, 0, and then I think we just put like that to make sure that we have done it correctly. 0 cosine of alpha and sine of alpha. Okay, and then 0 minus sine of alpha and then cosine of alpha. Okay, and then this one is 1, 2, 3, and then this one is like that, and then and then this one we give angle inputs in radians. Okay, so we don't change anything. So that's the rotation about X, which okay, and then we make rotation about Y, just so we can easily make the transformation matrix. Okay, so let's save space. Okay, so make a rotation about Y, rotation RY, rotation Y, and then in Y we have phi. I think this is what we discussed before. Phi, and this is phi. Okay, and here you have RY, you return the RY, and because you are doing Y this time, so this one, okay, what's going on? So you have cosine, starts with cosine, and 0 here, and then sine will be negative, and then that's it. That's a comment. And then here will be also 0 and 1, 1 and 0 at the end. Okay, and then 1, 2, 3. I think you don't need to do that. Let me check. If you, you need, so you need to end the, we need to end the row. So this is positive, and then here will be 0, and here cosine. Yeah, that's okay. Hold on. Okay, so this is correct now, and then rotation y. This is phi. So now this is phi, 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 phi. Okay, and that is alpha. So now we say this is z, and now this is z about theta, and this is z, and I'm changing the z. So now if it's z, so it will be on the z-axis. So you have, now this is negative, that's positive, and then because in the z-axis that's 0, and so now here will be negative. Here the minus sign, and now that's cosine, always like that. Positive is the sign that changes values only, and so this is 0, and then now that's, and then 1, 2, 3, go to the next line. So this is 0 and 0 and 1. Okay, so now you have rotation x, rotation of z, about theta, or z cosine sine 0 minus sine cosine 0, 0, 0, 1, and rotation y by phi. Y is here, should be, yeah, here, just alignment. Okay, so that's a cross because it's around y, and then cosine, cosine, minus sine and sine, that's phi, and then x alpha, so you have alpha about x, so it will be 1, 1, 0, 0, and here is 0, cosine, cosine, and then sine positive, and then minus sine negative. Okay, okay. Now we have the rotation, basic rotation matrices. And so now we say, for example, we have A. So now we are going to do, again, we're going to do the size of this one, because this is important in whatever input you give, and then we'll know the number of joints for that particular robot, given the transformation matrix. So we follow the transformation matrix of TZ D is equal to what? So you have, you input the TZ D with, should we also do TZD? Okay, maybe let's create a function also for TZZ. Okay, so a function of TZD, because it will be according to, okay, anyway, it's fine. TZD, and then we input transform what Z about D distance. Okay, so that it will be clear. Then you have a D, okay, and function and function. Okay, so now if you input the, now you have TZD is equal to the distance, input distance, okay. So now you have, what is this now? You have I 3 by 3, and then you have it's a column, so it's a 0, 0, and D. Okay, and that's your first three columns, and then now you have in this case 0, 0, 0, and then a 1 here, a 1, and then that's it. Okay, so let's check if we run, for example, TZD is equal to, what is this? Transform. Let's see if this is correct in terms of the size. D, for example, D1. Okay, let's check if this is correct. It will give you TZD. And then let's input this one, robot kinematics of alpha. Okay, so theta 1, maybe let's just say 0, 0. Theta 1, let's input this one. Theta is, in this case, let's just say 0, 0, 0, and then alpha is pi 0, 0, and then you have what is the next one? D. D is 0 0.5 and 0 0.4. Okay, that's fine. And then the other one is 0, 0 0.3, 0 0.3, for example, and then that's it. Okay, so end function, what is wrong? Slides, robotics M, line 33. What's wrong with line 33? Here. It's correct. 0, 0, and that's pi. What's wrong with this one? Here. Okay. Okay, let's try. Still end function. Syntax end function. What's wrong with this function? Okay, end function, this one. Still we have end function. Okay, this one. And this one. Okay, what else? No more. Okay. Where's this? Line 43, 43. I still have. Okay, let's increase it a little bit. No more. Okay, then, okay. So now you have the same thing as this one. Yeah. Okay, let's increase it so that you can see properly. The same thing as that. Okay, that's just what we're trying to get. So now you have transformation matrix D, Z, D, and then TZ theta. Okay, this is what we're trying to achieve. And so let's just do one by one. TZD and TZ theta. Okay, TZ theta. And so transform Z, and then you have theta. Theta, and then here theta. Theta, and then input angles in this in radians. Angles in radians. Okay, and then TZ theta, you're going to change that, and then we are going to do what? Transformation Z theta. You have the R of Z theta. R transformation, this one. Z theta here instead of I. That's Z theta, and then this one is 0 because there's no distance difference, and then that one is 1. Okay, let's check. So you have transform Z theta by theta. Transform theta by theta. Theta 1. 1. Okay, so it's fine. And then let's see. Then they should have phi. line 56. This is rotation Z. Rotation Z by, what's wrong with this one? I didn't correct it, theta. So Z by theta, and this is, okay, I didn't change that. So this is theta, 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 theta. That's correct now. And then Y phi, okay, alpha, okay. So Z by theta is transform Z by theta, basic rotation. Why? Okay, I didn't see that. Okay, now let's check. Okay, so now you Z by theta, and then now you theta, because theta is 0, so there's no change. Your theta, okay, let's just change the theta now. Instead of 0, 0, so 10, 10, and 10. Okay, so now you have some value of the rotation, and this was 0. Okay, that's fine. And this was the transformation of the distance. Okay, now, and then next, you have transformation Z distance, and then X by A. Okay, so that's the distance. Let's go here because this is the closest one. You can just copy dx a by a, and then you have dxa transform x by a distance. Okay, and you have a. And now you have identity, identity, and a here. A. Okay, and then here is 0, and the rest is 0 because this is distance transformation only x distance. So where is that? So we're going to call it so that we can test whether this is correct. Transform x distance, and then we do a1. Okay, okay. Then now, how come it doesn't show? This should be 3 transform x xa. Correct. It's a transform xa distance. Xa distance ia. That's correct. And dxa. Because it, okay, it should be dxa, and dxa doesn't return anything. Okay. No, now, okay. And there should be they didn't put an a distance. A is 0. Okay, so let's just put something a so that it doesn't. Okay, I mean, so that we can just enjoy seeing the values. Oh, the last one. There, it's 0.3, and this one is 0.4, and this one has the rotation matrix. Okay, so now there's a transformation about zx, z theta, xa, and now x alpha. So because this is z theta, let's change it to, okay, so this is x alpha. Okay, transform x alpha, and this one is alpha. Okay, so I wanted to see, to show you how I program so that you can see exactly what is needed. So basic rotation about z, about x by alpha. So x by alpha, and this is alpha, and nothing here. Okay, so now I think we're almost ready. So transform alpha. So let's just get here from transform alpha of 1. Okay, so you can only do it one by one. Okay, transform alpha. So here you have -1, which is negative. Your alpha becomes negative because you, I cannot imagine. Okay, Is it correct? DZD robot kinematics. How come it doesn't? This is 0.4, and this is the rotation of alpha, and then here the rotation about the x of theta, and this the transform of a x along a, and rotation of x by alpha. X by alpha is pi over 2. It should be pi over 2, not pi. Again, that's my common mistake. Okay, there, and then you can see, okay, instead of just a -1. Okay, so now I think that's correct now, and so let's create the transformation matrix. So the transformation matrix will be just all these. Okay, so we have to make this and multiply accordingly. So this is I, theta I, theta I, then multiply, and then mix. Let's make some, cut some lines so that, okay. So now this becomes, this is an I, and this is an I. So we have, this is the transformation of A. When you have, A transform A, okay. Transform A, and then you have transformation A. Then you have, you can come out with your A, okay? So that's correct now. So, but then this A is only the AI, okay? This is only the AI. So you have to keep on multiplying. So A, the size of A is a 4x4 matrix. Is we can say identity. How to say identity is a small letter, or I, yeah, I of 4x4. Okay. So now you can see, you can say for I. Okay, I don't know if this is, it needs. Maybe it's not. Is equal to 1 to what is the size n. Okay, and then you do this multiplication, and then you say AI AI. Okay, so when you do that, you transform the identity to transform to the next transformation matrix, and then that's your AI. Then the next one, whatever is your AI, it's transformed to the next one, and so it has the effect of, this is N4. It has the effect of doing like this. So let's just comment it. 0A, 1, 1 times 1A, A2 times 1A3, like that effect, times and so on, times n minus 1A n. Okay, so you're going to get the n effector transformation matrix there. I mean the position and then the orientation of the n effector. So now we are done in terms of forward kinematics. And so what we can do is that transform. We include, let's see if this is correct. We say the transformation matrix A is equal to, we call this, and I just give it exactly theta alpha DNA. And then there you go. Then the A will be given, the n effector position and orientation. So A list values are undefined warning code. Okay, undefined. Why are they not defined? Okay. Alpha I, D and A transform theta alpha.